let's jump in. Are there any questions before? Okay.
They're fine. Yeah.
Okay, I don't see any questions. So today I want to talk a little bit about an important application of optical design in recycling, resource recycling. And I'm going to focus on this article, which is actually posted on the website. So if you click, where is it? Yeah, here, this link leads you to this article. So you can read it yourself. I'm going to follow this. This is an article by Andres Nordbryn, who's a founder of a Norwegian company, which has been around for a little more than a decade, I think, where they have been developing technologies, primarily optical technologies for resource recycling. And it's a very useful article because, although it's a little bit old, it's a very useful article because it gives you an idea of an interesting aspect, an important problem, first of all, and secondly, an interesting aspect of application of optical engineering for this to solve an important problem, right? So hopefully you can draw the parallels to your projects as well. So essentially, the idea is to, optical technologies can be used to, the punchline is here, okay, optical technologies can be used to identify and sort recyclable materials in a way that makes efficient use of available natural resources and helps to reduce fossil fuel consumption, all in a cost-effective manner. Now, of course, we know that recycling and, of course, waste management itself is a pretty significant challenge in terms of volumes. We are generating huge amounts of waste, and the amount of waste that are being generated is exponentially increasing. So we need to have some way to deal with it rather than just using landfills for obvious reasons. And of course, reusing is and recycling, and there are various terms we'll talk about, is quite important. In fact, maybe that's the place I would start with, is maybe the definitions of various terms here, and then we'll jump into the actual details. So maybe we should understand when we talk about these terms, what do they mean? So reuse, of course, means the materials are reused over and over again, and standard examples of washable napkins, reusable coffee cups, reusable grocery bags, which of course are more common now. So that's obvious. Recycling, of course, means that the materials are essentially recycled into new products of the same type or of comparable value. So it doesn't have to be exactly the same. It can be a glass bottle that's cleaned and recycled, right? Or it can be aluminum cans that are melted and recast, plastic bottles that are granulated, cleaned, and remade, PET plastics that are made into polyester textiles, like the fleece I'm wearing, for instance, right? So lots of interesting examples there. Downcycling is another interesting term, where the materials are used for a lower grade product, so the price you can hope to achieve for a product like that will be lower than the original product. Examples are crushed glass used in landscape filling material, plastic from bottles used for flooring materials or park benches. I'm sure many of you are familiar with this. You can also deal with energy recovery, which is not terribly common in the US, but it is used in many other countries, particularly in Japan and a few other countries. I would say the idea is that the energy is generated in the form of electricity or heat from the process of breaking down waste source. As example, electricity generation through incineration, producing a combustible gas from waste, composting and things like that. Anaerobic digestion of material by microorganisms to release energy. So methane generation is an obvious, it's a common example of this. And finally, there's disposal, which is, of course, the worst situation, where materials are simply placed in landfill. So we want to try to avoid that. However, that's what happens in vast majority of cases. So, okay. So in any case, what we want to talk about today is basically to understand how optics can be applied here. So and we'll go through several examples. So one of the first examples is the idea of reverse vending machines, and all of you are very familiar with this. Essentially, if you buy a can of soda in the supermarket, it has typically there's a deposit associated with it. You pay an extra 5 cents, typically, depending on the state where you are. And after you use it, you can get back those 5 cents by depositing the can back into a machine or taking it to a recycling center, for instance, right? So the machine is nice because you typically find these machines in grocery stores or wherever you actually purchase these cans. And these are called reverse vending machines because they're the opposite of traditional vending machines. So instead of giving you the can, it takes the can. And there are various companies in the space, Envipco in the US, Wincor, Nixdorf in Germany, Tomra in Norway. In fact, Tomra is the company started by Andreas, who's the author of the article that I mentioned before. Now, of course, this is an important and interesting problem, right? One aspect of it is technical, and let's talk about that first, but there's another aspect of it is political, and how do you actually get people to actually use it, right? If I buy a can of soda at a supermarket, it takes me some effort to actually take it back to the supermarket to get that 5 cents back. So how do you incentivize people to do that? But let's talk about the technical aspect first. So technically, this is challenging because the idea is that there are many different kinds of cans, many different kinds of bottles, many materials, many shapes. So, the machine cannot be for a very specific product because that will defeat the purpose, right? You need to be able to accept all kinds of things. So when the machine accepts these different things, it needs to be able to identify that it is a valid can or a valid bottle or whatever. And it needs to also ideally be able to sort the waste into different containers. And thirdly, it needs to be able to store, significant amounts of these recycled materials, because you can't just do it one at a time. You want to be able to store it and have a pretty significant amount of these materials processed or sold to some centralized facility. So there's, the reason these machines exist is because, of course, these are for-profit companies, right? So someone actually has to pay for these machines to be there. So they expect some sort of return on their investment. And there are various ways they make that return. First of all, the idea is to be able to identify and sort the waste. And high speeds is something we'll come to later for these vending machines. Of course, high speed is not so critical, but sorting I wouldn't call it waste, but sorting this into, actually, sorry, I should make this full screen. Okay, so sorting this into different categories is, so first of all, identify, that's important, and then sort into different categories, because how purely or how accurately you can sort different kinds of plastics, different kinds of glasses, whatever, into the different categories increases the value that you can achieve by selling those categories or buckets, right? So that turns out to be a pretty challenging technical problem, which we can solve with optics. So this is where optics comes into play in terms of how we identify what material it is and how we classify what material it is. And nowadays, this is done with optics plus, I would add, machine learning, which I won't talk about in this class, but actually I'm going to be teaching a class in the spring where we will actually think about these things in a little more detail, if you're interested. And the issue of high speeds comes into play when we're talking about centralized facilities, which we'll talk about later. Okay, so, whoops. So first thing we want to think about is shape measurement. So here, the idea is to be able to recognize a can or a bottle, or if it's a special type of plastic bottle versus a glass bottle, for instance, right? So all of these can be thought of as a shape measurement technique. And of course, high accuracy is needed because you might have different types of bottles which are quite similar in shape. So you want to be able to distinguish them. And this turns out to be, of course, if you're going to automate this, not by a human being, this turns out to be a hard problem. And one of the first solutions people did was a very simple system where they had a simple conveyor belt, and they had a laser, which you can see right there, and then they have a detector. Actually, let me go back. The laser is actually standing up there, and there's usually a detector on the other side, which is you can't see in this picture, but the laser illuminates the detector. So this is the laser, and this is the detector. And when this path is blocked by a bottle, right? So at one instant of time, it goes down on the conveyor belt and it blocks the light. The signal is blocked, so you don't see it, right? You see a bip, a drop in the signal. So there's a peak signal, suddenly it drops a little bit, and the length of this drop in terms of time, if you multiply it by the velocity of the conveyor belt, will give you the actual length of this bottle, right? And of course, you can imagine different orientations to ensure that you get different shapes in X and Y and potentially in Z as well. And then doing some image processing techniques or data processing techniques, in this case, not an image, to able to detect the shape. Now, of course, this is a little bit, by the way, this is also what's done in garage door openers, as many of you might know. But of course, in a garage door opener, there's only one sensor and one laser and a sensor. But in a shape detection system, you will have many more of those. This turns out to be expensive and not as accurate as more recent approaches. More recent approach is something called a laser range finding. Here, what you do is you still use a laser, but the laser, instead of being a continuous illumination, it's modulated at some frequency. Okay, so you have a laser beam that's essentially modulated on and off, usually at some frequency. Then the laser beam bounces off some object and it comes back and it's detected. And the detected signal, I'm going to draw in dashed lines, is phase shifted. Why? Because the light has traveled, right? So you have the laser here, you have the camera here. Light has gone from here to here and bounced all the way back. So if this distance is L, the light has traveled a distance of 2L. So I would expect a shift in time of 2L, which is the distance, divided by the speed of light c, right? That'll be the seconds shift. And that shift in time for the light pulse to leave the laser and reach the camera can be represented by a phase shift here. And you apply some signal processing techniques, something like a phase lock loop or optical amplifiers and so on, to very precisely measure this phase shift and know what that time difference is, this delta t is. Now, by knowing the time difference delta t, right, I can measure that. And by knowing the speed of light, which I know very precisely, I can estimate what this distance is, L. That means I know the distance between the sensor and the object here. Now, by knowing that, as this object is moving by or the laser is being scanned, I can create a 3D map. So this L corresponds to the depth. So I can create a map of Z as a function of X and Y, which is essentially the surface of the object I'm trying to detect. This is called laser range finding. Now, this can be extremely accurate. It can be quite cheap if you use cheap lasers and cheap detectors and relatively simple algorithms. It can also be expensive depending on the precision, but you can also do it relatively cheaply. This is also very powerful because you can use multiple lasers and do big, very fast shape measurements. So this is an example shown here, which shows a 3D crate imager. So it's basically a crate containing beer bottles or something like that. And you have a laser that scans in an arc. So there's a source which essentially moves in an arc like that. and it sends light onto the crate, and of course the light bounces back. But all of this happens extremely fast, right? In picoseconds, right? 10 to the minus 12 seconds. So this scan is vastly slower. So you get a significant amount of signal as you scan in an arc, and then you create a three-dimensional shape of what's inside the crate. Whoops. Sorry about that. Let me guess that. So using this, of course, you can then map out, okay, what kind of bottles do I have in the crate? What kind of cans do I have? How many do I have? And things like that. So all of that helps you to essentially design the robotic system in order to do the separation. Now, I want to show one relatively simple example. It's a simple video that shows a very simple application of laser range finding. Let me see if it. Does that audio play, by the way? I know we have issues with audio sometimes. Can you hear the audio or no?
No, the audio is not coming, but
that's fine. I think I know how to fix it. I learned this recently, so let me. I'm going to share again, actually. Sorry about that. Share sound, okay. I think it should work now. Tell me if it works or not.
Welcome to the Callaway Performance Center.
Can you hear that? Okay, great.
I'm Deegan, and I'm one of the club fitters here at the test center. And today we're talking about an important piece of technology for Callaway Golf, the Callaway LR550 Rangefinder. And it's fairly simple to activate. Simply press the power button down and it puts the laser into continuous mode. And you can scan.
So you can see what's happening there is that
this particular pin
the laser is bouncing off that flag coming back.
So this takes a little bit of the guesswork out of the round of golf for the player. They don't need to walk around and look for a sprinkler head. Simply shoot your pin, get your number, and play on. Okay, so for those of you who play golf, you probably know this, but I was just wanted to show that this is an interesting application of this. Let me go back here.